So I want to first talk about the Coolest Concrete Award. As I said, it's the first one, and it was launched in September 2020, and it's intended to celebrate the art and science of concrete and to showcase its use. The entries were encouraged from those involved in interesting applications of concrete where only concrete would fit the bill. And the projects could be large or small, civil engineering or research-based. Now, we had 7 entries this year, from which a winner and a runner-up were awarded. And we would like to encourage the entries for this year's award to go forward to the FIB International Young Persons Award, to spread the word, as it were. And we're going to be holding the next, the Coolest Concrete Award, so the second one that we're going to do later on this year. Keep a lookout for it in the Structural Engineer. And I'd like to thank our judges for the Coolest Concrete Award, Andy Truby, who's going to be speaking later, John Armitage and Emily Halliwell, who very kindly put in the work to judge the competition. So I'm just going to go through not all 7 entries, but just the runner-up and the winner. And the runner-up was Will Hawkins. He's from University of Bath, now was at the University of Cambridge, and he's done a thin shell textile reinforced concrete floor. He was using textile rather than steel reinforcement, and the work was to reduce the embodied carbon of a floor system. And you can see from that small graph at the bottom there just how much embodied carbon he could save. So the next one up is the winner, and this is Camilla Samuelson, and she's won for her First Light Pavilion at Jodrell Bank, which is a really exciting project, and I'm looking forward to hearing about it because Camilla is our first speaker this evening. She's a project engineer for Atelier One, and before Atelier One, where she joined in 2016, she's got a master's in architecture and urban design and a master in structural engineering and building technology. So well done her, and that's from the Chalmers University of Technology. So I'm now going to hand over to Camilla to talk about the First Light Pavilion. Thank you very much.
Thank you very much, Jenny, for the introduction, and thank you also iStruct and fibUK for the award. I am very happy to be the winner of the Coolest Concrete Award this year. And I am now going to talk a bit about the project that I submitted. So the project is called the First Light Pavilion and is to be a visitor center at the Jodrell Bank Centre of Astrophysics outside Manchester, and it's currently being built at the moment. The architects were Hassel Architects, and I was involved in the structural design up until stage 4 as a part of the Atelier One team. And here in the image you can see the architect's visualization of the final building. And as you can see, it's a shallow dome structure and that is covered by a green roof. And the shape of the building was inspired from the large discs of the telescopes on site. And here we can see a floor plan showing the layout and the arrangement of the building. And it will contain an exhibition space, an auditorium, a cafe, as well as some offices. And the structure itself will be comprised of a curved reinforced concrete roof that is supported by circumferential walls. And in this smaller diagram, you can see the load-bearing walls highlighted in color. The total diameter of the building is about 50 meters, while the shell thickness itself is only 200 millimeters. The longest span is about 20 meters, which equals a span-to-depth ratio of about 100. This can be compared to an eggshell, which has a span-to-depth ratio of about 250. Due to planning regulations, the curvature of the shell had to be quite shallow, which resulted in large thrust forces at the edges. Unfortunately, the soil conditions were shown to be quite poor, which meant that we couldn't put any horizontal force on the foundations, and therefore also buttress walls was not an option. Instead, we worked with the circumferential reinforcement in the edge of the shell and the top of the wall to create a tension ring. And we also made use of the internal walls to help with the loads. And in these diagrams, you can really see the slimness of the shell in relation to the span and also the shallow curvature. The shallow curvature itself, together with the internal walls working as supports, was a major challenge in this project, since it meant that the shell was working partly in bending, partly in membrane action. And in this diagram, you can see the principle of the shell action versus slab action, and also how the circumferential walls were working as ties around the building. To fully understand the behavior of the structure, a quite complex nonlinear analysis method was required, mainly to fully understand how much it's working in bending and how much in membrane action, but also to understand how the stiffness is affected by cracking and nonlinear material behavior. And we was collaborating with, among others, Nick Nikitas from Leeds University on how to model the structure. And we also got a lot of valuable advice on the material behavior from Tony Jones at the Concrete Center. And in these diagrams, you can see the force and moment patterns of the shell and where we find a large tension compression and also moment peaks. We analyzed the structure in two separate software packages, Midas FEA and in Autodesk Robot. Midas has the possibility to take nonlinear material behavior into account by automatically considering cracking, but it's quite heavy software and normally used for smaller extracts of a structure and was not fully suitable for a large-scale model like this. Robot, on the other hand, does not take nonlinear material behavior into account, but it works well with large structures and it's relatively fast. So we made use of a method where we analyzed different design options and verified changes, first in Robot, and then we made a final verification in Midas and also local detailed checks. To be able to make an as efficient structure as possible, the reinforcement was divided into multiple reinforcement zones based on the moment plots and the membrane force plots. And this one of the advantages with using concrete for this project was that reinforcement can be added exactly where it's required by adjusting the reinforcement layout, and thereby avoiding using unnecessary material. Since the shell and wall had to work together as a tension ring at the edge, this connection had to be fixed and movement joints were not possible. To verify that we wouldn't get excessive cracking from shrinkage, we made sure that the soil would not provide significant restraints to the foundation. And we also made use of the waterproofing to reduce the friction, basically working as a slip membrane to allow the structure shrink as a unity. And to avoid excessive cracking during casting of the shell, we adopted a method where the main part of the shell was casted first, while leaving a strip at the edge to be cast at a later stage when the main part of the shell would have had the chance to cure and shrink independently. Making use of the curvature made it possible for the shell of the first light pavilion to be very thin, since a load path in pure compression and tension is a lot more efficient than a load path in bending. And I have included here a sketch showing the deflections for the curved roof of the first light pavilion. in comparison with a similar flat slab with the same thickness and span, but no curvature. And as you can see, the flat slab shows a deflection of about 40 times the case where the curvature is taken into account. And this means that making use of the curvature is a very efficient way of making an efficient and sustainable building. And finally, I would just like to show some pictures from site. And this is from when we went to visit in the autumn when they were casting the shell. And it was very interesting to see the full logistics and the complexity of the whole thing, since the shell itself had to be cast in one single pour. And here you can see how they are pouring the concrete onto the formwork. Overall, it was a very interesting project to be involved in, and also a quite complex one. And I learned a lot in the meantime, both about material behavior, about new softwares, and also about shell action. And that was all for me. Thank you very much for listening, and thanks again for the award.
How many days did you leave it for the joining strip between the wall and the dome and the shell?
So we were only involved up to stage 4. So the actual final design was with the contractor. So I don't know what finally was made, but we suggested that it would be left for, I think, 14 days. But it was only an initial estimate.
Okay, so sort of the same sort of time as you would do for post-tension slab, presumably. Another question, did you measure the deflection? Having calculated the deflection, did you measure it?
Since we were not involved at the end, we didn't, but there was a suggestion of having monitoring on the shell in collaboration with Leeds University. But I'm not sure if that finally was installed or not, but it was brought up as a suggestion.
Okay, so what was your role in the project?
I was working on the project as the project engineer, so I did most of the analysis and in collaboration with Chris Matthews, that was our associate director, and Neil Thomas, the director, but I did most of the analysis.
Great, thank you. I've got a question on whether did the final design differ from your design in any significant regard? Having done the initial design, did the final design differ from it?
When we spoke to them when we went on site, they said that they had kept most of our design. There were some adjustment in the reinforcement diameter, and I think they also had introduced us an actual steel beam around the edge as a tension ring. But other than that, they said it was similar.
Right. We're now getting lots of questions in. You'll be glad to know.
Yeah.
Some of which we won't be able to answer. Were there any waterproofing additives, admixtures, incorporated into the concrete mix? And what concrete mix did you use? I mean, particularly consistency, because you had to pour on the slope.
Yeah, unfortunately, I won't be able to answer that since I don't know what they finally did use. But it would be interesting for me to know as well what they used in the end. But that's with the contractor. So
yes, and who was the contractor?
It was Kier.
Kier, right. Okay, you might not be able to know the answers to this because it's a contracting question really. Is how did you manage to keep the slab thickness the same given the curvature and being one continuous pour?
Yeah, I cannot really answer that either, but they seemed to be quite careful on site with like flattening the concrete out and like. But yeah, I cannot really answer that. I think it's with the contractor how they monitor that.
Okay, and finally, because I think we've got to the end of our time for the questions. Did you make use of cement replacement cements? Do you know?
We suggested that was gonna be done to make it more sustainable, but yeah, as well, the final concrete mix was with the contractor.
Okay,
so.
Great. Thanks very much, Camilla. That was a really interesting talk, and congratulations on winning the award. I think it's well deserved.
Thank you very much, Jenny.
Thank you.